Well, very nice to be here. This is my first conference in forever. So it's nice to see everyone in the flesh, and also nice to see many people that I don't know. So I get to know a lot of interesting stuff while being here. So I just wanted to talk about more or less the role of accretion in forming gravitational wave sources. I guess for this audience, that title might be way too general. I really want to talk about binary mass transfer and how it can lead to gravitational wave sources. So I guess many of you have seen this. It's just an illustration of what LIGO, Virgo, and Kagra have seen so far. Well, not Kagra for the moment. And the main message out of this is that gravitational wave astrophysics has become commonplace. So with the detectors at their current sensitivities, when they're working, we get more than a weekly detection. And we're getting to the point where we have almost 100 sources, the vast majority of them merging binary black holes, mostly because of the biases of the detectors. But really, in terms of black holes, they have completely gone beyond what we know from electromagnetic sources. So given this, a lot of people try to explain how the systems form. This is a very biased selection of formation channels. We'll be hearing about AGN disks later in the week, for instance. And all these channels try to solve a problem, which is that stars want to grow big. But if you want something that emits gravitational waves in an efficient way, you need it to be quite compact. So moving forward, focusing on one of these channels, the common envelope evolution channel. This is normally considered to be called the classical channel for the formation of these sources. And it involves starting with two stars. One of them gets stripped and it forms black holes. And when the other one wants to evolve until it's roadshow, the process is unstable. It leads to common envelope evolution. And through this process, the orbit is hardened and you form your second black hole. Now, just so you know, in terms of how we actually model this in the community, there's tons of simplifications going into this. One of the big ones is that if we want to model millions of these sources to construct a population, we rely on very simplified methods for binary stellar evolution. So it's essentially a semi-analytical approach that relies on single star calculations. Now, the other thing is that even if we use detailed stellar evolution codes, they're still one-dimensional, and this phase is fundamentally three-dimensional. So in all cases, we need to rely on some simple approximation. This is the energy balance approximation, where we assume that the energy in a spiral is essentially what we need to combine the system. Now, an actual alternative to this is that in this phase, we can have a branching point, depending on the stability of mass transfer, which in turn is dependent about the structure of the star and how it responds. And we can instead get potentially an ultraluminous X-ray source, a source that transfers mass stably to the black hole. And also it was pointed out by Ed van den Heuvel that depending on the mass ratio, actually this mass transfer process can lead to orbital shrinkage and give you a gravitational wave source. So one thing that's been coming up a lot right now is that actually a lot of people are disfavoring a bit this traditional scenario. They think there's some fundamental issues regarding black hole progenitors, that they do not like to grow too much to where common envelope would happen, that their binding energies are too large, so common envelope would fail. And on top of that, from these simple calculations, this population synthesis, this mass transfer scenario starts to look more likely. Now, how exactly does this work? What is the physics going on in here? So we have this picture, a star throwing mass into a black hole. It throws at a given mass transfer rate. Material is ejected, a fraction of it. So most cases of interest operates on the thermal timescale of the donor star. Thermal timescale is tens of thousands of years, so that gives us very high mass transfer rates. Next up, if we consider typical stellar mass black holes, about 10 solar masses, then the Eddington rate of the black hole is far lower than more or less the mass transfer rates that we would get. So the common approximation in here is that mass transfer is very inefficient, and almost all the material, this beta is almost equal to 1, and it's ejected in a disk, in a jet that goes out very fast, so it does not interact with the binary. When that happens, this is something that briefly came out in the previous session. More or less, the angular momentum that would be lost from the system can be easily described. It's just the orbital angular momentum of the accreting object itself. And in particular, in the cases where the accreting object is much less massive than the donor star, its specific angular momentum is far higher than that of the orbit. So this can lead to very efficient angular momentum mass loss. Now, once one has this can be integrated, and you can get essentially the full orbital evolution under these assumptions. So for instance, we can get expressions like this that say what's the orbital period of a system. And the only thing you need to know is a reference orbital period, a reference mass ratio of the system, and the current mass ratio. So just as an example, we can think about a star, an OB star orbiting a black hole. It undergoes mass transfer and it's stripped to its helium core. And we know the initial orbital period and mass ratio. We know the final mass ratio, and from that we can compute its final orbital period. So this allows us to make some cheap population synthesis. We can just say we have a star, a donor of a given mass. What happens as it's stripped to a companion of another mass? So these are just some examples of doing that. This is considering a 30 solar mass donor star with black hole companions of different masses at different orbital periods. And essentially the graph goes in that direction as the donor is stripped. So we see in particular for the green line, a 30 solar mass plus a 4.5 solar mass black hole, this produces a very significant decrease in the orbital period, essentially 3 orders of magnitude in here. And for all these cases, the decrease in orbital period is sufficiently significant that it leads to delay times from gravitational wave radiation for a merger that are below a Hubble time. So this is more or less conditions that would allow for this to happen. Now, what happens if we consider slightly more massive black holes? So we bump up the black hole masses by 30%, and we get this. So the contraction of the orbit is still quite significant. This system that starts at 1,000 days ends up around 10, but the contraction is not significant enough to produce a gravitational wave source. The delay times end up being too large in the end. So mass ratio is an important ingredient in this. It needs to be extreme enough. And the other ingredient is that it needs to be highly non-conservative. So these dotted lines are the same results, but for conservative mass transfer. And again, one can see in here that the process is not sufficient to produce a gravitational wave source. Now, if one were to have like a form of outflow from the system, so outflow towards a circumbinary disk, for instance, that could be a more efficient source of angular momentum loss, then potentially that would act in favor of this. But it always needs to compete against the stability of mass transfer. If the orbit shrinks too fast, one will get a common envelope instead. And this was mentioned briefly before, SS433, galactic microquasar. And it was used a bit as a motivation for this in this paper I mentioned by Ed van der Heuvel, because it has quite an extreme mass ratio, this factor of 3 in a quite small orbit, and the system is known to be undergoing a stable phase of mass transfer, and it can be seen from its environment that it has been doing that for a long time. So it has been like that for thousands of years. Now the system shows indications of strong jets operating as well as circumbinary material going on in there. So maybe there's a potential for not just jets that would remove efficiently mass, but also circumbinary material that would help remove further angular momentum from the system. So more or less what I do in general is stellar evolution simulations. That's kind of my main thing. So I went ahead and tried to model bits of this evolution scenario. So one can think of this entire chain of events starting from 2 stars. They might undergo interaction, one forms a black hole, and then the other one does its part, and eventually one gets like a wide binary black hole or a merger. To avoid doing caring about all the uncertainties of this phase, I just started playing with simulations that start from this point. I start the simulations just putting a star and a point mass accretor to which mass transfer is inefficient. And I do this with the MESA code for stellar evolution, and just wanted to point out there was significant contribution to this from an undergraduate student, Calibro de Papas, in Northwestern University. So I usually like to make plots that show what are the outcomes of simulations. So for instance, I consider in here a fixed donor mass, and then I see what happens if I change the mass of the black hole in the system and the initial orbital period at which we consider them. So if I do this, there are two fundamental edges. If I go too high in period, there's no interaction. If I go too low in period, the system would interact at sums, and it's not really a feasible initial condition. Next up, I can draw just lines at different phases of evolution. So as stars evolve, they grow, and essentially at higher orbital periods, interaction starts at a later evolutionary stage. So one can do this kind of thing. And then from the simulations, ideally one would get an instability boundary that would change as the envelope becomes convective. And then one can ask the questions of whether or not this boundary goes low enough in black hole mass to allow for significant hardening. And on the other hand, which systems survive common envelope evolution? This is something I worked on as well, but I'm jumping for this talk, simplifying a bit the outcomes of that. This is the result of detailed simulations. This is considering a 30 solar mass donor at a very low metallicity environment, a 10th of solar. And just to guide your eye a bit, that's the instability boundary. All these things in here are common envelope evolution. And the mass transfer event, the stable mass transfer systems are marked in here. And more or less, there's this interesting band in here where we see that mass transfer is stable, and it also allows for the formation of gravitational wave sources. Now, another interesting thing is that through these simulations, we observe that several systems actually would overflow their outer Lagrangian points. So the donor stars in these systems, they do not have hard edges at their photosphere. They really have an extended atmosphere. Many of them have very large pressure scale heights in the outer parts, so they're very fluffy in the outside, and they need to overflow significantly the L1 point to transfer mass at the rate they want to. And in many cases, they will actually overflow the equipotentials of these outer Lagrangian points. Now, as part of the simulations, we actually extended prescription by Cole van Ritter for mass transfer through the L1 point to account also for mass being lost through these outer Lagrangian points. Essentially, if the star would keep expanding from this point and fill its outer Lagrangian point, this would act as a hole that would lose material in there. And similarly, if parts of this region are above L2, one can essentially think what happens if that mass, instead of being accreted over here, would just go and be shot out from L2. Now, one needs to do some approximations in here. In particular, we're just assuming that the specific angular momentum loss is just a specific angular momentum of that Lagrangian point. So this provides more efficient angular momentum loss. Now, what we see in this is that even though we get this loss, the systems remain stable. So it's just a small fraction of the transfer mass, typically 10%, that would essentially go into forming circumbinary material, but it does not destabilize completely the system. So this could go towards explaining something like SS433. Now, we can do several things with this. One thing I think it's relevant is trying to cover our tracks and see that everything is sensible. And this is work I've doing with several students. There's one that already published work the previous year on exploring this type of simulations to different masses, different metallicities. And what she sees when comparing to rapid population synthesis codes is that those codes significantly overestimate what common envelope evolution would produce for these sources. Next up, there's Matthias Fabria, PhD student in KU Leuven. He's essentially working incorporating tidal deformation into stellar structure. So essentially just how the star is being deformed by being next to a companion and how that affects the hydrostatic structure and potentially the stability. So he worked a bit on the basis of that. And one of the things we want to target in the future is this problem on how the stability of this boundary might be affected by this. And another one that's also started first year PhD student also at Leuven and at KITP is working on considering how this same channel might work to explain all different kinds of compact object pairings and gravitational wave sources. And some of these are quite interesting in terms of forming potential outflows throughout the Lagrangian points, in particular, when one thinks about white dwarf plus white dwarf systems. White dwarfs accreting at very high rates are expected to expand significantly and would naturally fill their outer Lagrangian points, for instance. So all of that was a bit theoretical. I think an interesting thing about this to try and substantiate this picture is to grab some observational constraints. I mean, getting more SS4s with these would be very nice. But another thing we can do is just verify. If this happens, then I need to have the initial conditions. I need to have an OB star with a black hole at essentially the right orbital periods. So essentially covering this span of initial conditions. And this is more or less what is rough positions for like the best understood high mass X-ray binaries. So they all seem to live like very low here. And this is very likely a bias from them being X-ray bright. That's how we observe them to be black holes. But in the coming years, I think this will be likely change all of this up. It's unknown territory, but I would say not for long. Already a few years ago, there was a system detected composed of a B star and supposedly a black hole companion at a period of 60 days. So much wider than this. I have my doubts about this in particular, mostly because they claim there is a H alpha emission that is associated to a black hole disk, but there's no X-ray emission coming from it. So it's a bit of a curious system, but I don't think there's any strong arguments other than that to disprove that there's something dark in there. Next up, just last year, there was a system with an O star of more than 20 solar masses, black hole mass of 6. And essentially in this plot, by the way, here I switched the x-axis to B mass ratio. It falls towards this unstable region. And there are two bits of work in which I'm involved with people in Belgium as well. One is work by Leuven Mahi, who has detected a system that has quite similar masses to this one, but at a slightly larger period. It's also an eccentric one, which makes it quite exciting to constrain kicks and black holes, for example. And also there's another one here by Thomas Schenner, which is actually an LMC system and would be one of the first extragalactic examples of a quiescent system, because for this one and this one, there are actually no X-rays detected. So as we start seeing all these things, I think one thing that we see is that they start populating this region and potentially providing a basis for a population that actually covers this set of initial conditions for this type of evolution. Now, one thing that we've run a bit into, more or less trying to observe the systems, characterize them, and potentially write proposals for Chandra, for instance, to try and see if they would be very dim X-ray sources, is that we do not have a good idea of what luminosities we expect for the systems. So there are arguments that just the von de Hoyle-Littleton accretion into black holes is not a good estimate because the angular momentum of the material that would fall into the black hole would be too low and it would not actually form a disk. But then the luminosity is expected to be low, but what exactly is low? And this is an important question in the moment for the people that are checking into this. And just to finish up, I wanted to point out that all of these sources are determined through spectroscopy. We're essentially observing the radial velocities of one star, in particular, all these quiescent systems operate like that. But one thing that will likely provide a very strong constraint on the properties of these systems and log periods is Gaia. So Gaia is more or less providing, I guess I don't need to explain what Gaia is, but it's essentially getting astrometric measurements of binaries later this year. The binary solutions will be coming out in June, if I remember right. And there's work, this is Tutkin Janssens, another PhD student at Leuven, and she has provided estimates on that essentially we'd expect to see over 100 OB plus black hole binaries in Gaia data that will have essentially measurable orbits. Now, that's already been mentioned by other people. I think the relevant thing about what Sutkin has done is more or less identifying the method to get the needle out of the haystack, essentially out of the billion Gaia sources. How do you actually go and identify the meaningful ones? So this is really something to expect just later this year. And with that, I would like to thank you for your attention. Thank you. Now for questions.
Okay, hello, thanks for a great talk. I have a question concerning your slide 10, which shows the prescriptions for the mass transfer and L2 outflow. Yes, my question is about the equation you have there. How will your answer change if there is a, say, 20 to 30% change to the prefactor in this equation, which would be motivated by, say, having a circumbinary disk that extracts angular momentum? And maybe more generally, what will be the effect of similar change to the L1 mass transfer? Say, 30% difference from what you use. Thanks.
Well, I guess for essentially the amount of angular momentum, it's true that more or less material is not being shot very fast from these points. It would be slower outflows, and one would expect them to be torqued by the binary system. So we did do some experiments to see what kind of effects would come out of this. I guess this is just, well, there's a bit more information going on in here, but it's just showing how this boundary for instability, essentially this line in here, is changed as we switch from considering the angular momentum of L2 being lost, 4 times this angular momentum, and even 9 times this angular momentum. So the thing is that the fraction of mass being lost without the Lagrangian points is just a fraction of the total. And what we see when we change these things is that the boundary slightly moves. So in the end, it doesn't change the final picture that much. Regarding more or less what happens if I understood right about the mass transfer through L1, I guess what really matters is the ratio of mass being transferred through L1 versus the ratio of mass being lost through the outer Lagrangian points. So I think that can also have an effect in here, essentially shift these boundaries. If everything is lost through L2, that would move the boundary significantly. But if one wants to consider essentially this range of systems that form gravitational wave sources, those would also shift together. So more or less that's also seen in here. The boundary moves to the right in here, but also this range of these light blue systems that represent systems that harden enough also moves with it. So I would say I have not been extensively thorough with these kinds of experiments, but at least my impression is that it would be robust to that.
So, yeah, I actually have 2 questions, but I'll start with one. Oh, here, Elena. Quick question is, how do you hope to identify black hole OB binaries in Gaia? Are you thinking to use the RUE, the goodness of fit of a single star, or?
So, I mean, the RUE is something that can be used right now to try and identify binaries. That's the data that exists. But in principle, if Gaia follows on the promise they've done, DR3 will have actually orbital solutions.
Yeah, no, I know, but the black hole and star, you wouldn't see the black hole. So how you identify the binary then?
So, well, you see essentially, even when you have 2 stars, you do not see the 2 stars. In most of the Gaia sources, you just see the photocenter of both stars moving around. So the thing is that when you have black hole companions, they would essentially tend to be, they don't have a light contribution. So essentially the photocenter lives further out. And the main way in which these binaries would be distinguished in Gaia is because their motions, the motions of the photocenters would be much more significant. I think that's the summary of what Sutkin did essentially and tried to identify the systems. That's the critical thing.
Okay, thank you. Can I ask a second question? Anyone else? Okay, then I'll keep it.
Thank you for nice talk. And so you have considered stable mass transfer or mechanism to cause accretion. But so OB stars has a strong stellar wind, and also Roche-Lobe overflow doesn't work anymore in eccentric binary if the orbital eccentricity is non-zero. So my question is, which mechanism is dominant? Wind accretion or Roche-Lobe overflow in such a massive star binary system
So
that you have considered?
So I mean, for wind accretion, when you have OB stars with black holes, usually the mass transfer rates are quite low. So they're very important for the phenomenology of the systems we see. The X-ray binaries we observe are essentially powered by wind accretion. But since the amount of mass that's actually transferred is very low, it doesn't play much of a role in orbital evolution. But when you have Roche-Lobe overflow, even if it's in an eccentric orbit, the system will, if it's trying to expand significantly compared to this orbital separation, it will try and shed its outer layers. And the amount of mass that goes out through that is far more than what you get through wind accretion. So I don't know if that answers your question. Significantly less in terms of total mass, but very important in terms of phenomenology, because it also drives long-lived phases of evolution that we actually observe.
Question here.
Yeah, I have a question that's a bit more tangential to your theory aspect, but you mentioned that MWC 656 has H-alpha emission, but no X-ray. So are there some emission lines known that are good tracers for accretion in black hole binaries?
Sorry, some emission lines that could what?
You mentioned that MWC 656 has H-alpha emission, which you found surprising because it doesn't have X-ray. But what are good accretion tracers for such black hole star binary systems?
I guess that I can say what's the argument for the black hole in there. So essentially, they observe this H-alpha. They can also observe the radial velocity of the B star, and essentially the ratio gives you the mass ratio of the system. From that, they can essentially estimate what's the mass of the star associated to the H-alpha emission, and from that estimate, they conclude that they would definitely see a star of that mass. They wouldn't just see this H-alpha. There should be something else.
All right, so the H-alpha might be more the B star, so the accretion just from the B star maybe.
Well, but it doesn't follow the radial velocity of the B star. That's the thing. It's in the opposite phase.
Okay, one more thing. Are there any questions online?
Okay, I think we have a couple more here if there's time, or do you want to defer those to the discussion session?
Just short question. Thank you. Yeah, so all this effect, overwhelming for me, a lot of things. But all this effect you talked about, in particular, the stability of the mass transfer when you have a lot of mass accretion, from more massive to small. You point out this could be stable. Overall, they tend to reduce the predicted binary black hole merger rate, right? Could you That's my sense. That's the impression I got. Could you give a sense, roughly how much reduction in the predicted rate you have? Or
So, I mean, I guess
they don't go through the common envelope phase anymore, right? You go through this, right?
yeah, but in a way, as you kill off common envelope systems, you gain some of the systems that harden.
Okay.
So there's a bit of a balance.
I see. So you don't get, if you don't have or hard to say which way it goes.
Yeah. And we more or less there was a bit of a study by the student that I mentioned, Monica Gallegos Garcia, that she was saying that normally the overall rates come lower more often than not, but there are instances where one would expect them to be relatively similar. But the thing is that these other simulations would essentially completely get off what the actual pathway is, even though they get similar numbers in the end.
Why don't we stop here and thank the speaker again?